Good morning. This is our morning session from today. So it is a pleasure to present the first speaker of this morning session, Professor Tohru Ozawa from Waseda University. He will speak about 2D Zakharov, I think, equation.
Thank you.
Please.
Thank you for the introduction. Buongiorno e buonasera. Thank you for the invitation, and I'm very happy to see you, everyone. Okay, this talk is based on my recent joint work with my student Kenta Tomioka. But this doesn't mean that this work is not a joint work with Zakharov. Okay. So let omega be an open domain R2, and the boundary is sufficiently regular, by which I mean that Laplacian restricted on see infinitive functions with compact support is essentially self-adjoint and extends uniquely to self-adjoint operator with domain H2 intersected with H01 omega. And the equation I consider is a system I u plus Laplace u equal to u, and Lambert b equal Laplace squared. Okay. And here, u is a function on time in space with values in complex numbers, v with values in reals. So we consider as a scalar system, and easily extends a vector system. Okay, so this is the assumption on the boundary includes the existence of bounded extension operator from L2 on omega to L2 of R2, and Sobolev spaces of order 1 and 2 separately. And okay, it means that the usual Sobolev embedding Galliard-Nirenberg inequality holds also on this omega. Okay, so it means that this u and v vanish is expected to vanish on the boundary. This is Dirichlet zero boundary condition, as well as we impose initial condition U0, V0, and dt V0 is given by functions phi, phi0, and phi1. And we always refer this triplet with function spaces they belong. Okay, we have many standard books, but here I refer the textbook of Catherine Srem and Pierre-Louis Srem. And also I have Zakharov's Chinese book on Zakharov here. Okay, which I bought on the bookstore near the Peking University. Okay, so the first result is Srem and Srem, 1979. They proved the existence of.
Sorry, Tohru. There was a question. There was a question in the right-hand side of the equation for U. This is V times U.
Yes, V times U.
V times U. Okay. Okay. Thank you.
The existence of weak solutions without uniqueness and the existence of local solutions in H3, H2, H1 in R2 by compactness method and energy estimate. And soon afterwards, added proves the existence and the uniqueness of global solutions in the space H3 and H2 and H1 intersects with H1. H1 function applies to Laplacian. In R2 as well as in a general domain with phi. This is a 2 squared, strictly less than 2 over C0, where C0 is best constant of Galiot-Nirenberg of this type, U squared, nabla U. This is the best constant, C0. Okay, and their solutions satisfy UT in H2 plus V T in H1 plus dTv in L2. The norm is bounded by constant exponential sort of a constant with t squared. And the method depends also in compactness method. And resist Galway. That's why we need t squared. In the original paper by Regis and Galway, where they studied cubic nonlinear Schrödinger equation in two-space, two-dimensional domain, where the bound is double exponential. Here, thanks to the quadratic structure, the result is t squared. Okay. Now here is the main result. Okay. Let phi psi 0, psi 1 in the domain H2 intersected with H01 and H0 and minus Laplace half of L2. Then and L2. Okay. L2 intersected with half Laplacian applied to L2. And the same restriction to over C0. Then there exist global solutions, strong solutions. Strong means U, V, and dTV belongs to this function space at any time. And moreover, we have the new global bound T H1 plus dTV in L2 is constant times exponential Ct. Okay. This is the main result. And here is the method of proof. Essentially, this is independent of compactness methods and also Blaise-Galway inequality. But that's why we have obtained the usual Gomor type estimate. And to be more specific, this upper bound is obtained by modified energy for H2 node. This method was previously obtained with joint work with Nicola Pisilia in 2016. And we propose regularized system for the original system Z, Zakharov, and prove boundedness of sequence of solutions of regularized system and boundedness in a space H2, H1, and L2. And we prove that this sequence forms a Cauchy sequence in somewhat weaker space, H1, L2, and minus 1/2 Laplace, L2. If we can prove boundedness on the Cauchy sequence in a weaker space, we first obtain the limit in this weaker space, and then with the help of integral equation, and this helps the regularity of the limit in the original function space. Okay, so let us briefly remember the conserved quantities. In order to present modified energy for H2. Okay, so we have conservation of charge and energy. AT 0. Here, the energy is defined as committing. Committing time variable nabla u squared plus 1/2 v squared plus minus Laplace minus 1/2 dv squared plus v is a scalar product in L2. This. So the proof is very simple. Here we have I u I dtu minus Laplace plus u minus vu. This is the equation, so this vanishes, and this IU is I is a generator of a gauge. So almost everything, including this Laplace and VU, is pure imaginary. So this vanishes, and we are left with d dt squared from this one. And similarly, the generator of time translation is simply dtu and dtu plus Laplace u minus vu. So vanishes, and for technical reason, multiply minus 2, then this vanishes, and from this part, we have nabla u squared plus here we have can make dt u squared. So first we write this form, and we subtract dtv u squared. And the last term minus dtv u squared is written at least formally minus dtv and Laplace u squared. And I use the second equation and minus Laplace t v t squared v minus t Laplace. So this is exactly equal to 1/2 d by dt, and okay, minus Laplace 1/2 appears here in here, dtv squared plus squared. Okay, this is a formal proof of the two conservation laws. And here we consider similar quantity for H2. This, of course, we cannot expect rigorous conservation laws. it's because it is closely connected to the integrability of the original system. So we cannot expect the actual conservation law, but we can we have the possibility to obtain substitute. Okay. Before that, why this is sufficient for H1 control? Energy implies H1 control. Let us briefly recall simple facts by Helder, U, and Forno. And this by the Galliard-Nirenberg inequality C0 V U nabla U, and this is written as C0 divided by 2 phi by charge conservation, and 1/2 V squared U. Okay, so and here 2. Okay, so the coefficient, the first coefficient is strictly smaller than 1, and this indefinite term is somewhat absorbed. So this that's why we can control H1 norm by energy conservation. Okay, so how about H2 norm? The basic strategy is rather simple. First, you start with something including H2 norm squared, and then differentiate in time and use several integration by parts and equations, and you have a preliminary result. And if that suffices for Gromwall type estimate, it's done. But in less favorable case, it's not enough. Then there are many, there must be many terms, and something's good, something's bad. And if you have bad terms, then you should write it in divergence form in time, ddt. Bad terms, if you had a bad term, plus. And we need two properties. One is that this is should be a part of the energy, and it's so it's a kind of a renormalization of the energy, and it's harmless, should be harmless in the sense that this new term is does not change the equivalence of normalized energy, modified energy, with the original quadratic part of H2 norm. And the other property we need is that rest terms is at least quadratic, so that the Gromov type estimate still holds. Or if this is not okay, we can admit it up to logarithmic correction, and in Bridge-Gallwey argument, or log, for instance, log E, log E. This can be handled. Instead, we have to pay the price that the resulting a priori estimate is exponential like that. Okay, so, but here I start with some easy a priori bound. The result is this. PDE squared plus log V squared. So let's start. And this is equal to the this real part, and this is imaginary part of I dt squared plus dt squared V minus Laplace V dt. Here I have used integration by parts once, and this is equal to, with the help of the first equation, minus Laplace u plus vu dt u, okay, and Laplace u squared dt v. And this Laplace u is real, so this vanishes. And time derivatives, this time derivative applies to u, gives cancellation, and we are left with I made yeah, okay, this is one. And okay, dt the imaginary part of dtv and the u and dtu. Still we have dtv plus u squared. And here we use equation again. So the result is u, and here I have I minus Laplace u plus u. And the same. Laplace u squared. And we have dtv and I put this Laplace u squared first, and then the other part of u bar plus u, and then plus 2 b u squared. And this is equal to Nabla u squared. So let me write it this way. So the second is d du plus dv squared plus Nabla v squared then f prime t is 2 dt v and Nabla u squared plus v u squared. Okay, so we write dtu squared as follows. But this is again by equation. Then expand the 2 no to your part plus u plus u. And this factor is written as minus Laplace squared plus plus nabla U squared. Okay, with this combination. And then we continue to write it in this way. Nabla V, nabla U squared. Okay, and this one plus 2 V nabla U squared plus V. Okay, so this
Sorry, Tohru, the last line in the right-hand side, what is written? VU?
VU.
VU, and it is L2 norm.
L2 norm, yes.
Thank you, thank you.
So this new modified energy is written as follows. PT V squared plus nabla V squared. Okay, so we have two indefinite terms. And we have to prove that those two terms are harmless. Okay. So V nabla U squared, this is equal to nabla V L2 norm and U L4 norm, L4 and U L4. And this is estimated by nabla V and U in L2 1/2 and nabla U and U in H2 norm, where we have applied Galliard-Nirenberg inequalities to L4 norm of U as well as nabla U. So 1/2. Then the result is okay. This H1 norm are controlled by a constant, and we are left with two factors, which comes from quadratic part of F, and the total exponent is 3/2, so strictly less than quadratic, so that's okay. And the next one be nabla U squared again nabla U L4 norm. So in the same way, we have by Galliard-Nirenberg inequality. So the important part comes only from this H2 norm. So the total exponent is 1. This modified energy is equivalent to H2 norm. And H2 norm of U and H1 norm of now H1 norm of V and L2 norm of DT V. Okay, so we are left with this right-hand side. Now U squared plus V U squared. Then we have dTV and nabla U to 4 plus dt plus dt dTV plus V in L2 and U in L infinity. And this is bounded by dTV. And in the same way as this, so nabla U H2 norm here and V and the U in L2 norm and H2 norm. So the result involves H2 norm and H2 norm. So the result is quadratic, and the whole Gromov type argument works to provide H2 control. Okay, this is only a formal proof, and the actual proof is start from this regularized equation. IDT UN plus Laplace UN JN JNV JNU and dt squared Vn minus Laplace Vn equal to Jn Laplace Jn-un. Here Jn is 1 minus n Laplace Yoshida approximation. So we need self-adjointness of this Laplace operator. And this regularization reminds me the regularization proposed by Irving Segal first, and then double convolution regularization by Juniper-Bello. And this formation preserves Hamilton structure of the original equation. So this is the starting point of actual proof. And I stop here and thank you for the attention.
Thank you very much for your nice talk and also for the fact that we turn back to traditional representations and traditional didactics. So as yesterday, we ask first our colleagues from internet if they have some questions. It is sufficient to switch on the microphone and put some question.
Well, I have one question. I ask?
Please.
So, I was wondering, for large data, is it known blow up above the smallness condition on L2? Or it is unclear?
Smallness condition is required to control H1 norm by usual energy. I'm afraid that I can understand your question.
Do you have blow-up result for large data?
Blow up. For instance, self-similar solutions were constructed by Frank Merrill, and I don't know the complete answer, but here is I'm looking for something on this Chinese book that I have.
While you're looking, Nicola, did I change your question or this is what you want to ask?
Yes, this is the question.
Okay. But you can read Chinese?
Yes, a little. So yeah, here is some results on blow-up solutions. And yes, it seems like I don't know the original one, but here is explanation of and proof of blow-up solutions, and it is due to in some specific situation, Villiers type argument works, and there is an existence of blow-up solutions with the large data.
Okay, thank you.
Thank you very much. This is really nice. Viral works. Some other questions, remarks from internet side or from also from the audience here? Neumann, for example.
No, Neumann aveva 0, un altro positivo per fare sì da approximation. The scheme is pretty much standard, no? So why not to?
There is a small question here from Alessandro. The question is, can we
No, well, okay. So just curiosity. So can you hear me? The scheme is pretty much standard. You see the approximation and so on. So you can replace. I was wondering whether one can replace your Dirichlet Laplacian with some other kind of Laplacian with boundary condition that still ensure you that you see the. So that's still positive, of course. That's to be positive because for you the Laplacian, the Dirichlet Laplacian was used at 2 levels. All this business of integration by parts because it produces no boundary terms.
Yes.
Whereas other Laplacians do produce boundary terms, but you are in a high regularity space, so you may control them as well. And then you use it for the approximation because you do the usual business. So I was wondering whether similar results are available, could be produced
For different Laplacian.
So what is the importance of this Laplacian? Why this
Yes.
physics Laplacian?
Probably, may I be closer to the microphone and explain? The question is, in your construction, you used Laplacian with Dirichlet condition.
Yes, yes.
Also you see the approximation everywhere.
Yes.
Laplacian. In this construction, is it crucial that you work with Laplacian with Dirichlet, or you can do the same scheme for more general cases of, for example, square of Laplacian or some other type boundary conditions? Is it correct?
Sì, sì, è trasparente la Laplacian di questa storia.
I didn't check it, so we should check everything, and of course, in the old paper by Added and Added, there is they introduced Neumann type boundary condition, but they only says we can study these boundary conditions, so no without details. So we should start from almost nowhere, and I didn't try it.
Okay, thank you. So it is possible to, but has to be done rigorously as they did. Okay, some other questions, remarks? Let's check also in chat. I think there is no more question. So for this, let us start. Let us say thank you to the speaker again.
Thank you.
Now we shall